Momentum.
Um,
Like a force is something you can kind of feel, right? I mean, you push it pushes back. I can kind of wrap my brain around that. Eventually, we'll get to energy. That's pretty difficult to try to like put something physical to. But where does momentum fit in that? It's somewhere in the middle, maybe. You see, that anybody? I didn't watch it, but I heard in the playoff game yesterday that Mahomes got concussed by the linebacker from the Browns. So that linebacker, Mac or whatever his name is, he had momentum and he delivered it to Mahomes, the quarterback. So if you're not a football fan, linebacker kills quarterback, sends him out of the game with a concussion. He had momentum. Well, what is it? Could a little bitty, like 190-pound running back have the same amount of momentum as like a 300-pound lineman?
yes.
Yeah. So the mass, littler running back, big, huge lineman, they can have the same momentum. And you said if one's going faster than the other one, so obviously mass and velocity are the key factors. But is it like what is it? What is momentum? Mass, you could say, is the quantity of like atoms in an object or something along that line. But is momentum like that? Can't really like. Yeah, it's just an equation. It's like a construct that we put together. And one way that I think about it is, so it's really defined as the object's mass times its velocity, and it's the symbol for momentum is P. I think P obviously can't use another M in the same equation that has M for masses. But P, I think I read somewhere once upon a time that said it's like from some Latin or Greek word for moving power. So they chose to use P. Did they use rho for it, really? No, but you had your hand.
Yeah, I was going to say, could momentum just be like the amount of force you would apply to something?
So there's clearly a connection to the amount of force you can apply, and this thing being the product of your mass and your velocity. So we could take Sam and put him on a skateboard and just give him a gentle push, and if he bumps into me, I'm not worried about it. But if he's on a skateboard and he's coming at me at 50 miles an hour, I'm going to do my best to get out of the way because I know it's going to hurt more, and hurt we usually associate with the level of force involved, right? So I think of it as like a measure of how hard it is to make something stop. Or you could think about it as how hard it is to get something going. So it kind of sort of sounds like inertia again. And because it is related to mass, it sort of in a way is related to inertia. It's a vector thing because it's based on velocity, not just speed, but it's based on velocity. So momentum toward the door in the room, if your momentum was 100, it wouldn't be the same as if you're going towards the windows if it was still 100 because one has to be negative and one has to be positive based on direction. So momentum, you need to incorporate the velocity sign if there's a reversal in direction for the velocity at some point. So, and there's no units, unfortunately. There's not like Joule for energy or Newton for force. It's still kind of a pain. The units would be kilograms times meters over seconds. So kilogram meter per second. It's basically how it's usually pronounced. There's not really a good shorthand for it. Once upon a time, some student in one of these years wanted to call them pentums because momentum is a P on the left-hand side, and they didn't want to say kilogram meter per second every time. I'm like, if it makes your life easier, fine. Don't do it on the AP exam, though, because if they, for whatever reason, were going to pay attention to units, you're going to get dinged if you get in the habit. So no abbreviation, not pentums. And so then impulse kind of takes us into section 2. I'm going to like lump all this together and then come back and kind of like break it down. And because an impulse, you probably have in your notes, has something to do with how much force is applied to an object and how long it's happening. It takes a long time for a train to go from 0 to 20 meters per second or 45 miles an hour. So they're delivering a force from the engines for probably many, many minutes before it gets to that speed. On the other hand, you guys know what a rail gun is? So a rail gun is like an electromagnetic, usually like huge accelerating thing. They're talking about like trying to launch satellites into orbit using a rail gun. And I think they're called a rail gun because they're typically mounted on railroad cars so that the recoil of the force of this launch that's going to be like massively strong force-wise. So if you launched it somehow with electromagnetic propulsion or something, you could get it to 45 miles an hour in a few seconds probably, but it would take a huge force to make that happen in a small amount of time. So there's a connection between force and time, but no matter what, the impulse delivered to an object is literally equal to what? I'll give you a hint. There's something called the impulse momentum equation. So I see you making a J with your finger. Is that what you're doing? Yes. Because the train could go from 0 to whatever its final momentum is from that force and time accelerating the train. Well, that product of the force and the time is called the impulse delivered. And if that end momentum was from 0 to whatever it is, it's kind of conceptually not that much of a stretch to say the impulse is equal to the change in momentum. And that's what the impulse momentum theorem states. So because an impulse literally changes an object's momentum, it's literally equal to the momentum, and therefore the impulse units would be the same as momentum units. So J is your unit for, or not your unit, but your symbol for impulse. Delta P, because they're equal, could also be thought of as a symbol for impulse. You don't usually do that, but where did it really come from? Newton never ever said F equals ma, full stop. Newton said the impulse delivered, or no, sorry, he said force is the timed rate of change of momentum. The time rate of change of momentum. So changing momentum with respect to time. I don't know if that's exactly how you did it, but F equals ma could be rewritten as F equals m times delta v over delta t. If we just rearrange it, we get F times delta t equals m times delta v. And that's the impulse momentum equation. If they're literally equal to each other, then we could say, if I said, well, if that train delivered 10,000 newtons worth of force for 100, let's make it easier, 200 seconds, 10,000 times 200 would be like 2 million or something. Couple zeros, 10,000 is 3, 2 more is 6. Yeah, 2 million kilogram meter per second. So if the impulse was 2 million kilogram meter per second, we could say that the impulse, mv, is equal to 200 million, and solve for v, maybe how fast would you be going if you had a 2 million kilogram meter per second impulse. You could say, solve it for v by putting in 2 million on the left. If you said your change in momentum was 2 million, you could put that in for the right, and if it was 90 seconds, you could solve for how big the force would have to be to get that to happen in 90 seconds. So there's a lot of like interchangeability the good news is here, it's a lot easier to keep track of than it was with the rotational stuff back when we were substituting V equals R omega and omega squared R for alpha and all that crazy circular motion stuff. So both of these could be thought of as impulse. And we could say J is equal to F times delta T. We could say J is equal to M times delta V. So when a question just says, what's the impulse if an object goes from 0 to 60 meters per second in 5 seconds? It would be 300. The impulse would be, I don't know how I just got the numbers, but I said from 0 to 60 meters per second in 5 seconds? I don't remember how I got to 300. Let's restate the question. Let's say that there's a 60 Newton force and it lasts for 5 seconds. What's the impulse? 60 newtons times 5 is 300. Now, there is one alternative unit form. You could say an impulse is Newton seconds, newtons times seconds. That's a little easier than saying kilogram meter per second. So you could use that interchangeably if you like n times s. Units could be Newton seconds. And this really would turn into Newton seconds if you multiply kilograms times meter per second. You could do some substitution and some cancellation and whatnot. So that's kind of like the basic rearrangement kind of stuff that you could do with force, time, and velocity and stuff. And if we look at, this is where they destroyed things. If we look at a constant force like what I've been describing so far, then it's pretty clear that the area here would be equal to the force times the time duration. So that tells us that from a force time graph, we could get the impulse. So area equals impulse. We could say the area equals m times delta v. We could say the area equals f times delta t. So if we knew, what these numbers were, we could kind of do different things with it. Well, what if it's something that goes like this? This is delta t, and force is over here, and we wanted to know what the impulse was from 0 to delta t. You couldn't find the area if you had a function for the curvy line, right? So how do we do area from calculus? Derivative or integral? Rate of change is derivative, right? So the rate of change is usually that slope top. Have you got the integrals yet?
Just starting.
Just started. Okay. So you want me to give you the whole long, remember how you had to do that f at b minus f at a or whatever that nonsense was? So I think I talked about this a long time ago, but if we divided this up into little bitty rectangles where they have little bitty changes in t's down here, and you can just take the heights and think of these as rectangles. If we extended this one up and then colored in all of this space right here, you can use that delta t, and then that height is the area. If you do that over and over, you get an approximation. It's not a very good one because you'd have this extra little bitty section outside of the curve. But if you keep making those vertical rectangles skinnier and skinnier so that they limit to almost zero width, then that reduces how much of this external space here that is not in the actual rectangle itself. So that's the new limiting process that you're going to learn to calculate area. And if you sum up all of those triangles, then you get the area, rectangles, you get the area in there. And we've done basic integrals in here, so we're not going to do anything more complicated. So the impulse equals the integral of f dt, the d instead of the triangle for delta t says that these are really small increments of time. But in the end, you would have to have had a function to integrate, like x squared. If f was x squared, then you do the integrate, raise the power to 3 and divide by 3 for your final integrate answer. So that's another way that we can find our impulse. So let's look at a couple of examples that'll be nice geometric shapes instead of having to do any integrating. A couple little things I'll just make comments on. Those examples in 9.1 and 9.2. Look at the one for 9.1. What page is it on? I don't know. 221, somebody says. No, what is it? We're just guessing.
It's that or it's 220.
224. I mean, when I say example, I mean not E and P, but example from the reading. So 224, blending over to 225. So an impulse, one other thing I didn't mention was impulse is usually defined as a very short duration, pretty in time, but pretty large force interaction. So collisions, car collisions, or baseballs hitting, baseball bats hitting balls, golf balls hitting, things like that. So 6 milliseconds, be careful, notice that means 6 times 10 to the minus 3 seconds. So milli, that prefix, 6 times 10 to the minus 3. The area here would be equal to the impulse. Well, what could we do with that? We could say if I could find the area of that, which I could do a 1/2 base times height to get an area. The question might be like, how fast does the ball leave the bat or something like that. In this case, it's asking like, how big is this peak force? Why do they go up and go down? If you think of slowing this down a bit, like with a tennis ball and a tennis racket, it's going to go whoop, and squish that ball and whoop, and it springs back. Probably not going to be a linear thing like this. Probably going to be more like some of the other diagrams that have this rising, like bell curve kind of shape thing. But anyways, so just a couple things that I wanted to point out there. One, get used to seeing things like milliseconds because these are short duration things. Pay attention to sign changes. The ball, they're calling ball moving in the left-hand direction negative, and then when it leaves, it's going in the positive direction. And so how do we get to F max? Think of this equation here as saying 1/2, this is really the base, and this is the height. So I'm not sure why they ran it in that order, but there's your 0.006, 6 times 10 to the minus 3. So I just wanted to point out a couple of those little things that are important if you want to get anywhere near the right direction for your answer. And then 9.2. 9.2 looks like a trickier problem. So basically, here's another one of those AP kind of questions where they can blend in some kinematics to impulse and momentum. So you have to do kinematics to figure out the speed just before it hits the floor, and then through the whole impulse momentum thing. So you're going to find the area. You're going to find the area. Is this the same? No, it's not the same problem. The area to figure out what the impulse is. So area is going to equal your change in momentum. And the symbols, the way they write their equations sometimes confuse people. I'll go back to the last page. Change in momentum is going to be, think of it as P final minus P initial, which is MV final minus MV initial becomes all that stuff over there, equal to the area. So they broke it down into 2 parts, and then you can just do the final minus initial thing. But sometimes they make it really confusing. Maybe not to you, but it was to me when I first got this book and was trying to figure out what they were saying. This is that same thing. This is saying J equals P final minus P initial. It's just rearranging it. So P final minus P initial. If they bring the P initial over to that side, then that plus the impulse is equal to P final. So when you see those, like, where did that come from? That's all it is. Okay, EP number 4, and then, well, shoot, so much time? No, 21. Let's do EP number 4 together. And go to lunch. All right, so this is fun of a graph. As some of the other ones look like they're going to be easy to work with. So we got these little negative areas here. Trying to think of what that might even represent. Forces in the negative direction, and then it flips and goes big time positive, and then back the other way. Maybe something is attached to a spring or something. So, what do we want to find in 4? What is the impulse that experiences the force shown in 9-4? How would you approach this? We really only have to do one thing, but 3 times.
Find an area.
Yeah. And this is a negative area. It looks like the one on the other side is exactly the same. 2 seconds. Yeah. So you can just do it once and then double it. But it's negative. So do the above 0 area and subtract off the 2 below 0 areas. I do have an answer, so when you get it, let me know. I'll pause this so we don't have a bunch of dead time. So what I came up with was a half, negative a half for each of the 2 below 0, below the t-axis, plus 6 for the big triangle above it. So 6 plus negative 0.5, again, 5, and I like the Newton second thing personally because I don't want to write kilogram meter per second. And what am I really working with as well is I'm working with force and time, so why not call it that? Anybody else call that? Did I do my areas right? Do 5,000. Why did I get 0.5?
I think we did see where it said that.
Oh.
Same thing. It's at the very end of the graph.
Very good. Yeah, these aren't 2s. These are millis. So 0.002 times 5 on negative 500 is negative 0.5. No, it isn't. It's got to be
You missed the
0.1.
half.
It's
You missed
negative.
the half.
Plus a half. Yeah, there it is. Thank you. Okay, so that is the right answer. I just forgot about the millis myself. And from there, we'll go to homework after lunch.